Good morning. It's 11 o'clock in Philadelphia, and welcome to Thermal Live 2016. Today is the second day and final day of this year's event. I'm Graham Kilshaw with Electronics Cooling Magazine, and we are the creators of Thermal Live. This presentation is Wearables and Touch. Cutting-edge solutions are never too hot to handle. Brought to you today by UICO. And I have with us our speaker from UICO, Joan Sullivan. Good morning, Joan.
Good morning, Graham. Thanks for the introduction.
You're welcome. We're also joined by the senior editor for Electronics Cooling Magazine, MP Divakar. Morning, MP.
Hi, good morning. Good morning to everyone on the bridge, and good morning and a big welcome to our audience.
Yeah, I see we have audience from all over the world logged on live, as usual. Welcome to everybody. If this is your first time at Thermal Live, I'm going to walk you through a couple of details so that you can get the most out of the presentation. Questions. If you have any questions during the presentation, simply use the Q&A box, the Q&A button at the bottom of your screen. You can enter those questions at any time. We'll collect them during the course of Joan's presentation. And then at the end of the session, Joan, along with MP Divakar, will go through all of your questions. We'll try to answer as many as possible. If you do have any technical issues during the presentation, just go to the yellow tab on your screen, and most of the common issues can be answered there. Within Thermal Live, you do have the ability to chat with the other attendees. Just use the group chat button at the bottom of the screen. That's a nice feature. You can view all of the presentations remaining for Thermal Live. In fact, you can still register for the presentations that were given yesterday, and you can receive a link to the on-demand recordings. Just go to the chain link button at the bottom of your screen. If you hover over it, you'll see that it's linked to Thermal Live. And the one next to it that also is shaped like a chain link is a direct link to the UICO website. So that's how you get the most out of Thermal Live. I can see we already have a couple of questions asking when will the slides be available. We always get that question. The slides will be available to download in 1 to 2 days from today. But if you want to rewatch the video recording of Joan's presentation, that'll be available within 1 to 2 hours after the presentation finishes today. But no need to email us, no need to request it. We will automatically send you those links to rewatch the video and to download the slides as soon as they're available. So no need to email us on those. And with that, I'm going to hand over to Joan. And I think we're all really looking forward to this particular presentation on some of the thermal management issues surrounding wearables. Joan, I'm going to pass over to you.
Thanks, Graham. Good morning, everyone. Welcome to the presentation. So my name again is Joan Sullivan. I'm a senior FAE at UICO, the makers of DuraTouch, the providers of the only all-weather touch solution. So touch, of course, is ubiquitous in most consumer electronics devices today. We see touch in all of our tablets and cell phones, and the reason it's the most common user interface is because it's simple, easy, and dynamic. It's very easy for designers to have an interactive experience with their users, and touch is essentially growing. We see it in everything from large-scale industrial devices to the smallest fitness bands and wearables. So let's go through and have a quick look at the overview of what a touch system looks like. When I refer to touch here, I'm essentially talking about a capacitive touch solution. Capacitive touch solution is made up of two main parts. The first one is the controller, right? The controller is a touch IC. Our controller has our DuraTouch firmware on it, all of our custom algorithms. The controller has an analog front end that actually measures data off of the sensor, an ADC that converts that analog information, and the firmwares that process the data that comes off the ADC. The touch controller also interfaces to the host CPU on the main device. So, we basically convert a position of a finger into an XY coordinate, and send that information up to a host CPU, typically over an I2C interface. The other important part of the touch system, of course, is the sensor layer. Now, the sensor layer that you can see over on the side over there essentially has a few different components too. It may look like there's nothing actually on top of your display on your cell phone, but there's actually a substrate layer that's either film or glass. And on that film or glass, we've sputtered indium tin oxide in a specific pattern. Indium tin oxide, more commonly known as ITO, is a transparent conductor. This conductor is basically a printed circuit on this film or glass substrate that gets put on top of the display in your system. The ITO is sputtered into a printed circuit pattern that essentially acts as an array of capacitors across the glass. So it's an array of capacitors, and that's basically the sensing layer. The sensor can be either discrete or on-cell. That essentially means when it's a discrete layer, you have it as a separate substrate on top of the display, bonded to the display through a optically clear adhesive. An on-cell layer means that it's been built into the top layer of the display itself. If you're familiar with most display structures, they essentially will have a glass substrate with ITO on top of it as part of their manufacturing process. So now that ITO just gets patterned according to the requirements of the capacitive touch sensor and gets built into the display itself and can be sold as a complete module. So the main problem with touch is that quite often users experience very poor touch functionality when they're in harsh environments. Simple things like sweaty fingers, trying to use their devices in the rain while they're wearing gloves, or in very hot or very cold conditions can cause significant problems to most capacitive touch solutions. Another big issue, of course, is power consumption. As our devices get smaller and smaller, the batteries in them get really tiny as well. And now you're trying to have always-on touch, so your watch or your cell phone wakes up the moment you touch it. But that means you need to be scanning touch all the time and still have a battery that lasts for days and not just hours. And of course, when you're talking about consumer industry, cost is king. So the cost of hardware is often a big barrier to people actually implementing touch in their products. So let's start with some of the common concerns about temperature. Rapid changes in temperature often cause touch to fail, and there's two different ways you can see these failures. The most common is false touches. So you can actually have your cell phone sitting on your desk, and if it got really, really hot, or it got left in a very hot car and the temperature changed very rapidly, it may see a false touch somewhere on the sensor, even though no one actually touched it. Or there was a big change in temperature and someone's actually trying to use it and it didn't actually detect any touches. This is very common in cold conditions. Let's have a look at why that actually happens. So the way capacitive touch works is the analog front end of the touch controller is trying to identify the difference in signal on the capacitive layer between a touch and a no touch state. So essentially, when you design the capacitive layer, we have, you tune it and you have your algorithms in there, and we basically measure the capacitance in our design and say, hey, when I see an ADC value of X, I can assume that there's not actually any fingers on the touchscreen because that's how I've designed it. This is what I expect the value to be when no one's touching the sensor. So then when a person comes in and actually touches the capacitive layer, what that does is makes a really small change to the overall capacitance of the sensor. It's in the order of a few picofarads. It's very, very tiny. But basically, the analog front end identifies that very small change, converts that to an ADC value, and we can detect when a finger is actually touching the sensor or not. So that little image I have over there shows you the difference of basically a touch versus a no-touch state in terms of ADC counts. So the problem obviously occurs when a rapid change in temperature happens to the sensor, and that no-touch state changes. So where we expect it to be is maybe X counts, and now it's jumped up to X plus 500 counts. And the system, of course, does not know that it's really hot. All it's seeing is a new ADC value that's much higher than what it expects to see, and thinks that maybe there's a touch on the sensor. So what we typically do to handle a problem like this is we have a baseline. So the baseline tracks where touch is at the no-touch state, where the sensor is when it's not being touched. So when the temperature starts to change and the capacitance value creeps up and the no-touch state begins to change, we also drift up our baseline to track the no-touch state. So we're always looking at a delta between the touch and no-touch. So even if the baseline has shifted dramatically or even slowly, we track that change. And then when a finger comes down, we can actually see the difference between the touch and no-touch state. Another big problem we have with capacitive touch solutions is water. The big problems are trying to use a touch screen when there's water pooling on the screen, or when you're trying to use it out in the rain and there's water rolling off of the edge of the screen. That often triggers false touches on your device. Cell phones and things like that, we don't take it out into the rain. We put it in our pockets and protect them. But if you've got a wearable, a fitness band, you may take it swimming, you may take it out in the rain, and it needs to actually work at all times. And the big reason for this is for most capacitive touch solutions, water and a finger actually touching the sensor are completely indistinguishable. As I said earlier, basically your ITO layer on your substrate is a large capacitor, right? It's an array of capacitors. So when a person comes in and touches it, you're adding capacitance to that sensor, and that small change is what's being measured by the analog front end. Now, basically, water is almost exactly the same as somebody coming in and actually touching the sensor. You put a drop of water on the screen, it also has a small change to capacitance, and the analog front end will detect that and say, hey, the capacitance changed a tiny little bit. That probably means there's a finger on the screen. And the goal of our firmware and our algorithms is to basically identify the difference between a finger and water and say, hey, no, that small little change that you're seeing actually doesn't mean there's a finger on there. It's actually just water. And we've done this through years of experience in the industrial sector and outdoor environments where our devices are used on fish finders and devices that basically spend all their time outdoors getting wet in the rain, getting seawater all over them and salt water. And we can identify the difference between a finger touching the sensor and water on the screen. Another big issue with capacitive touch is working with gloves, right? Most PIC gloves just will not work when you try to use your touchscreen on your cell phone. Quite often, people sell these conductive gloves with a little bit of conductive thread in the fingertips to actually get it to interact with the touch sensor, right? Or they have, when other solutions try to combat the problem of detecting fingers through gloves, they kind of ramp up their sensitivity, and that causes, false hovering touches. So these are kind of big problems, and we at DearTouch think that touch should just work at all scenarios. So even if the user is wearing like a big fat winter glove on their, on their hands, and some of you out on the East Coast will definitely notice that when you go out in the winter and you've got your big gloves on, you have to take it off before you can actually start your cell phone up and actually call someone. And we don't think that should be an acceptable solution. So, why does this actually happen? if you look at the structure, again, of the capacitive touch sensor, we have the capacitive layer that's projecting a field out into the air, right? Now, it's not just going straight out into the air, because typically you have a cover lens layer on top of the touch sensor, and that's protecting the ITO, and that's basically giving the finger something to touch. So you have this capacitor that has a glass overlay on top of it, and that's basically the dielectric material that the capacitive field needs to propagate through. So the thickness of that dielectric material impacts, of course, the type of field that you're projecting. So if you have a really, really thick dielectric, then it becomes harder for you to project your capacitive layer, to project your capacitive field and actually be able to identify a finger. And essentially, when you're wearing a glove, that acts as an additional dielectric layer between your finger and the sensor. So your finger forms one plate of the capacitor, the ITO forms the other plate of the capacitor, right? It's a parallel plate capacitor. And then that field that gets formed in between them gets changed depending on where the finger is and how close the finger is to the other electrode. And that's the difference we're trying to identify. So now if you have this big cover lens glass that's maybe a couple of millimeters thick, and then maybe a wool glove that's another couple of millimeters thick, now you suddenly have 4 to 5 millimeters of material between the two plates of your capacitor. And now your field really needs to be able to propagate out pretty far to be able to identify a finger. So again, a very common solution by a lot of capacitive touch providers is to just simply ramp up the sensitivity, and they're just projecting this field out really far. But that obviously is a challenge. So if a hand is even hovering over the sensor now, you're going to pick up false touches and have unintentional touches on the sensor. So that's a huge problem. So one of the things we like to do is to use a combination of rate of change algorithms and hover detection to really identify when there's actually a finger there, like a very sensitive finger that's a very small finger, and maybe it's really far away, but we can still pick it up and really only identify it and detect it and report it to the host when it's actually touching the sensor. And the only way you can do something like this is when you have really good SNR, because the moment any noise comes into that measurement, you're going to have a lot of trouble. So you need to be able to distinguish between thermal changes and water changes to identify the small little gloved finger in between all of those noisy situations that your sensor is picking up. So one of the other big problems with most capacitive touch solutions is power consumption. Wake on touch is a requirement that's getting really big in consumer devices today. So they don't want users to have to hit a button, specifically a physical button, to wake up the device. They want the screen to be turned off and then just have the user touch or swipe on the display to wake up the display and wake up the rest of the system. Obviously, that means the touch controller IC needs to continuously be scanning, because it needs to be looking for a touch all the time. It basically sits there in kind of an idle mode, scanning periodically, does a scan, looks for a finger, doesn't see a finger, goes back to sleep for a little bit of time. And then it wakes up after a timer runs out, does another scan, looks for a finger. And if it does see a finger this time, it says, okay, I see a touch, sends that report up to the host, wakes up the display, wakes up the host, and then the system can actually start going again. So from a power consumption perspective, at a system level, that's really great, because you can allow the touch controller to run by itself and turn off, your heavy power-consuming devices, like the display can get turned off, the host can get turned off. You're just running the small little touch controller. But obviously, the only way that works is if the touch controller itself is very low power and really has a lot of clever power management, so it's not, running unnecessarily. It's not turning on when water hits it, for instance. I've got a fitness band, and every time I wash my hands, water touches the screen. Now, if water looks like a finger and the touch wakes up the display every time it sees water hit the screen, that's a problem because you're waking up your device unnecessarily. You're consuming a lot of system power. And you need a device that's really robust that can both, run for a really long period of time without consuming a lot of power and doesn't have problems when you're trying to wake it up. Again, thermal changes, right? When you leave your phone in a hot car for hours and hours and you've forgotten it in there, and then you need to get in and use it, suddenly if the temperature swing has, it's gotten it so hot that you can't actually touch the device and wake it up, you're going to have all sorts of problems. You end up having to reboot your system, and excessive power consumption can cause all sorts of problems and have just basically have a very bad user experience for your customer. So DuraTouch is in devices that have week-long battery life with Wake on Touch. So we've got touch that can scan at a very slow rate, but basically wake up the display and wake up the system. And some of these devices can last for a week. So we have some very good algorithms to handle power consumption. The other big problem with consumer devices using touch is the cost of capacitive touch hardware, right? UICO has solved this problem by using a lot of single-layer sensors, which lower the processing cost and have a thinner stack in the Z dimension while still having better performance. So what I have over here are 3 different types of stack-ups that are quite common in industry. So UICO does designs in all 3 stacks, but typically we do stack number 3, which is the single layer stack. That's again, very low processing cost and has a thinner stack for really small wearable devices. You can make them really thin. So typically what you're seeing, let's look at stack number 1. Right on top, what you have is a cover lens. That's the substrate that the finger actually touches. So that one can be, either glass or plastic, anywhere from 0.8 millimeters up to 4 millimeters thick, depending on the application. That's usually bonded to the first layer of PET with PET substrate with ITO sputtered on top of it, and bonded through an optically clear adhesive. Right? So if you have a 2-layer structure, you may have 2 layers of PET or 2 layers of glass. Both of those layers have ITO on them. This forms your capacitive touch sensor. They can be bonded together through an optically clear adhesive and then bonded to the cover lens material with an optically clear adhesive. So you can see that can be a fairly thick structure, which is fine if you're a large device that's mounted on a wall or something like that. But if it's a smaller device like a cell phone or a wearable, something like that takes up so much space in a tiny little device, and consumers don't want to be that thick. So typically you'd go into either the B or C stack, where it's usually a single layer of ITO, maybe a layer of ITO with bridges to basically get a 2-layer touch sensor without actually having a second substrate layer. But ideally, if you can be really clever with the way you print out your capacitive layer and come up with a very clever pattern, you can actually do the entire sensor on a single layer of PET with a single layer of ITO sputter without requiring any metal bridges to transition from one layer to the other. So to sum up, UICO solution can work with thick gloves in wet conditions, when the sensor is dirty, through extreme temperature swings, and with super low power consumption. Essentially, DuraTouch provides touch that works everywhere. UICO's touch technology is patented science of sensing software. We have tons of proprietary signal processing algorithms that live on our DuraTouch controllers. We've spent 7 years developing these algorithms. We've perfected them in very harsh environments, and now we've ported them over to wearable devices we've basically made a low-power version of our technology that can work on very small devices that have, 7-day battery life. So the next thing I like to do is step you through a few videos of our technology working in a number of different environments. Yeah, so this video is basically of a Kohler shower. It's a high-end shower that has a capacitive touch sensor on it. It's basically controlling the temperature of the shower, the water flow, and it has gallons and gallons of water pouring on this touch sensor. So obviously, you cannot afford to have any false touches on this, because if you do, you're going to scald the person in the shower, and that's just completely unacceptable. So this Kohler shower has our touch controller in it. It has our touch sensor in it, and basically can work even with tons of water pouring all over it. The next video I'd like to show is our touch with thick gloves. So a big tablet application with huge work gloves, essentially, that we just picked up from Home Depot. You can still use this touch sensor. You can swipe, you can tap, you can pinch and zoom with a really, really thick pair of gloves. And you can try that on most of your cell phones, and you'll find that that really just won't work. So we started off with our technology in these kind of industrial spaces with, even home automation or large tablets and large devices that were plugged into walls and consumed a lot of power, but that was okay. And then we took those algorithms and ported it into a really small, low-power package and put it into, for instance, a watch form factor. So I've got a little video of one of our eval watches, and we'll show you what that looks like with water pouring all over it. So even with water pouring over the screen, you don't have any false touches, and you can still continue to interact with the device. You can still use it, you can swipe. So it can both distinguish between water on the screen and a finger. So, we've seen a lot of devices like the new Apple Watch, they're advertising it as waterproof, and it's great, and it's awesome, but the moment you actually get it wet, all they do is turn off the touch. They're saying, oh shit, I see water, I can't deal with identifying a finger anymore, so they turn off touch, and now you can't actually use your watch. But our solution allows the touch sensor to both identify when there's water on the screen and when there's finger on the screen, and distinguish between the two, and still be able to use the device when there's tons of water pouring all over it. So the next video I'd like to show is basically again, glove performance on a wearable device. We essentially have an off-the-shelf Moto 360 that doesn't use our touch performance, and you'll see that when we try to use it with gloves, the touch just doesn't work, and that makes for a very poor user experience. So what we're wearing here is a very standard motorcycle glove. For instance, a bike glove. You may use this when you're outdoors, when you're on your motorcycle, and the Moto 360 didn't work, but our watch just continues to function even when the user's wearing that same thick glove. So GeoTouch offers two different types of solutions. The first one, again, I've talked about is the touch screen that most of you are probably familiar with. It's the transparent substrate with the transparent ITO conductors sputtered on top of the substrate, and that goes on top of a display, so you can see the display through this. It's called a standard touch screen. One of the other things we offer is GeoTouch Surface. So this basically allows us to put a touch sensor, a bendable, flexible touch sensor on top of anything. It could be on a steering wheel, it could be on a joystick, it could be on, it doesn't have to be on top of a display, and we can still sense through a, wood or plastic or even fabric, really, any non-dielectric material, we can still sense through that. So you can be really creative with where touch can be put on your device. You don't have to be restricted to putting touch directly on top of a display. On a wearable, for instance, it can be in the band of the wearable. If it's a plastic band, you can put it inside the band and still be able to sense touch through the plastic of the band. There's really a number of different things that you can do with that. When we look at the stack up of a standard GearTouch touchscreen, UICO provides, quite often the entire module. We can provide the touchscreen module, which is the touch sensor layer, the ITO touch sensor, plus a controller that has all of our firmware on it, fully tuned to work with that sensor. We provide an integration support. So if you have a cover lens requirement, you say, hey, it needs to look like this, it needs to be this thick, we can source it, we can build it, we can assemble the entire stack, we can bond it to the display, we can bond it to the cover lens, and give it back to our OEM as a complete stack up. We offer support with multiple operating systems. We've supported Windows and Linux, Android Wear, as well as a whole host of custom operating systems that our OEMs have used. And GearTouch Surface, as I talked about before, is bendable and flexible touch. We sense through, again, all dielectric materials. So, it can be plastic, it can be leather, it can be wood, it can be, it's wrapped around a steering wheel and completely invisible to the user, but still getting input and that data that can be sent to a host, and you can do all sorts of creative things with it. This GearTouch surface still continues to work when the user has gloves on, when the surface is wet, when there are extreme swings in temperature. Things like automotive, cars get left out in the heat all the time. You need a touch solution that can work with dramatic swings in temperature, and GearTouch has proven time and time again that we can work in all environments. And I think that's it. Yeah, thank you for attending, and if you have any questions, please go ahead.
Thanks, Joan. That was a very interesting presentation. I think without a doubt this whole subject of wearables is going to be an increasing challenge for folks in the thermal management space, so we look forward to seeing more on this over the coming years. Attendees, I hope you also enjoyed this presentation. If you have questions for Joan and this particular subject, now's the time to post your questions. You can simply use the Q&A button at the bottom of your screen now. Send those questions in, and Joan and our senior editor for Electronics Calling Magazine, MP Divakar, are standing by to answer your questions. And with that, MP, I'm going to hand over to you to begin the Q&A portion of this session.
Thank you, Graham, and it was a very nice presentation, John. We all enjoyed it. So one thing that I would like to comment is I think we in the electronics cooling and thermal management community, for the most part, we deal with, I would say, heat transfer and the solutions for that problem, predominantly, for active devices. These are devices that switch on and off and have some dissipation, but often what happens is we overlook or maybe neglect cooling, thermally managing passive devices. So your presentation is an excellent example that it is indeed, a problem that deserves recognition and solution thereof. So going through the presentation, I recognize something, and I think what you have is, at least from our perspective, is an excellent thermal management solution for touchscreens. Is that a fair statement, to interpret?
Yeah, absolutely. Any device out there that's using touch, temperature is a big part of a problem that they need to solve, right? You can't tell your users how to use your device. You can't say, oh, I'm sorry, it only works in room temperature. And quite often in consumer devices, you don't have room to put in some large heat sinks, and when your GPS has been on for hours and hours and it gets really hot, the entire system heats up and the touch sensor heats up, and you essentially need a touch solution that can handle these changes and doesn't run into problems. So, even though not necessarily we're not acting as a heat sink, we're not dissipating anything, but we're coming at it from a different direction. We're saying, hey, we get it. Things are going to get hot. There's only so much you can do. Now, what can we do to solve that problem? How can we deal with these temperature changes and still give the user the proper touch experience?
Okay. Can you explain, what are the typical problems on the cold end of things? Let's say, minus, 10 degrees or 20 degrees Celsius. What happens to the ADC count? How much does it shift on the cold side?
Yeah, absolutely. So let me just jump back to the slide. Yeah. So, as I was saying before, we typically have what we consider like a no-touch state, right? So the no-touch state is basically, when you think about it from an ADC perspective, a certain value that's coming in, and we're saying when we see this value come across the ADC, we're assuming there's no touch on the sensor. Now, the problem is when the sensor gets really, really cold, that reference value can drop, right? So when it drops so low, you put a finger on the screen, the deviation we see, the small capacitive change that we see due to the finger is so small that it doesn't actually push us now over the threshold to actually identify the finger as a touch, right? So, the graph I have over here shows you like a very straightforward scenario. When I put a touch down, you can see this nice little peak. So I can put a threshold somewhere in the middle of that and say, hey, the moment my signal goes over this threshold, I'm saying, okay, I see a touch, and that's really a real finger. But now if the entire thing shifts, 200, 300, 400 ADC counts below where I expect it to be, suddenly my threshold is now way higher than the change in signal, and you just simply won't pick up a touch. So you can be, desperately poking at the screen, and it doesn't know that there's anything happening, so it won't report position to the host.
Okay. Somewhat related question, and that is there any preferred, temperature where you calibrate, the touch versus no touch states?
Yeah,
or
so
is it just the room temperature?
It's typically room temperature. It's typically calibrated at room temperature because realistically, that's, for most consumer devices, that's where it's being used like 95% of the time. So again, the way we tend to work with our solution is we have a baseline that can track these changes. So we're not just we're not just taking a standard reference and saying, hey, this is our reference, this is where it's going to be, and any change from this calibrated area causes all sorts of problems. So even though we calibrate at one level and we tune at this level, we have this baseline that can track temperature changes, and therefore we know when our threshold also needs to move with the baseline.
Okay. The other question I had is, I think it was on your slide 18, where you have the complete stack. I think this is the solution we were mentioning a few minutes ago, where you can give the complete touch interface solution or your own Dura touch layer, to compensate for any custom application. This is a way, what I call as a back-end type compensation, because the correction happens after the touch sensation has taken place, right? So is there a better solution to shift it to the front, or doesn't make any sense?
Yeah, so I mean that's an interesting question, and I think that's fundamentally the idea of the way a capacitive touch sensor works, right?
I see.
Basically, you've got a capacitive sensor. All it's really doing is, it's sitting there, sending out these capacitive fields into the air, and then looking for, a disturbance in the field. And that's really the only way it can identify whether there's a finger touching it or not. So it's putting out these, the fields are just getting propagated up through the cover lens, and then it's just looking. It's just blindly looking, and any time there's a change in that field, it basically goes in and analyzes it a little bit more carefully and says, hey, is this change due to a finger, or is it due to water, Or is it due to noise? Or is it due to, something else? Like, is it a temperature change? Like, what is this change actually being caused by? So really, the sensor itself is quite dumb. It's not doing anything very intelligent. All of the intelligence comes in from the firmware on the back end. So that's why you kind of need to be really clever with your algorithms to look at the sensor and say, hey, how do you distinguish between a finger and any one of the millions of other pieces of noise in the environment? Because really, if you're just trying to build something that identifies a finger, that's quite easy. The problem is trying to identify the difference between a finger and everything else that could also cause a change to this capacitive field.
Okay. Well, one more question I had was, is there any special attention that is being paid to, the controller, the way it is mounted at the back end of the sensing interface? Is there any special glue or thermal interface material that you guys are using that is temperature, thermally or temperature-wise stable, or is this something proprietary?
Yeah, so actually a lot of that is proprietary. The adhesives are very, it's an interesting, quite a proprietary part of the industry, and less on the controller to the PCB or to the FPC. But the other one that's quite important is the OCA layer that bonds the cover lens to the sensor. Now that is something that needs to be thermally very stable as well, because again, when it's exposed to UV and it's exposed to temperature changes, if that adhesive gets either discolored, or if temperature changes cause the adhesive to melt again like that, this is completely unacceptable, because your device will shift or it'll look bad, or you'll end up with air bubbles between your sensor and your cover lens. So we do have custom adhesives that allow us to combat a lot of these environmental conditions, and thermal is definitely one of those.
Okay. I think that's just about the questions I had, and I don't see anything from the audience so far. If there's some other comments you want to make while we still have a few minutes left, feel free to do that. The audience may think of a question or two in that meantime.
No, I don't think I have anything else to add right now.
Okay. So if not, I think we'll wrap up. So thank you again, Joan and Forrest. It was a very interesting presentation. As I was commenting earlier, predominantly we address the active cooling solutions or active devices. Mm-hmm. And though passive is not something that we ignore, we do, but it represents a smaller percentage. But we at Item Media and Electronics Cooling, we recognize, the expanding ecosystem of thermal management, and we're glad to host and see these kind of presentations, and we'll address those topics more and more in the coming days and months. So it's been quite a refreshing experience to see this presentation and a slightly different topic for our audience. I hope they all enjoyed it. As before, we will put all this presentation and video content on our website. So all those who are registered, you'll get an email update. Feel free to sign up if you haven't for other events today, and also yesterday. You can time travel, so to speak, and look at the cache versions of Thermal Live from yesterday. I can tell you, this was my first year both taking part and also hosting. It was a fantastic experience, and I will make sure I will not miss this next year. Again, have a great day, and we are on to our next session. So thanks, everyone, and this is a wrap. Bye.
Thank you.